Perfect. And I guess you all can hear me. Last night of the conference, thank you for staying. And thank you to the organizers for having me. So I want to tell you a little bit about the, let me see if I can get this working. It's okay, I'll use the pointer. This was supposed to connect to the, this is the one, right, that I should use to switch slides. I don't know if it's working. I have my own. Let's see if it works. It's all right. Let's just go. For some reason, the computer decided to not work today. Is this? Oh, is this Zoom? It's literally Zoom. Sorry. Okay, I can see now. What's the problem? And I guess this is going back and forth. Okay, all right. I'm back. So I still remember the first time I ran my first galaxy formation simulation. Coming from doing some work in computational cosmology and supernova remnants, I thought galaxies, come on, how hard can it be, right? So you set up your initial conditions, just get all the basic physics in, and you add it to your model. Star formation, just simple star formation. And you just decide to look at the most basic parameter, or perhaps the most fundamental you can think about when you think about a galaxy, the stellar mass and its evolution over time. You see this beautiful disk kind of evolving here. And then you decide to double check, how is the simulation kind of doing? So you read over the literature and you realize that order of magnitude, you can assume some efficiency for the conversion of basically baryons into stars. And you expect your simulation to be over here, right? About 10 to the 9 for this specific halo in this particular time, like a specific time strike that I'm showing you here. So you read more and you realize that actually stellar feedback, star formation kind of drives that self-regulating feedback loop. And that should drive your stellar mass down to this 10 to the 9 kind of order of magnitude that I mentioned. The problem is that you run your model with supernova feedback and your stellar mass shows up here. So this is kind of not working, right? And then you start to read more and more, and you realize that actually these models have some problems. It could be resolution. We know we're missing physics. So the solution generally has been this thing that we call calibrating the models. You go into your physical parameters that you try to select to be in some way loyal to reality, and you start to crank up the numbers. And so you boost your supernova feedback. Once again, the videos are not showing. I don't know why. Okay, they're back. And now you get your stellar mass kind of in the right order of magnitude, specifically for this halo. This is the domain where we should have our stellar mass. So this is actually working, right? The calibration works. But then you start to look at your galaxy and you see that you don't have this nice, beautiful disk anymore. The feedback seems to have this kind of breathing modes where you blow up the entire galaxy once you have star formation events. So that's a bit fishy, and then you continue reading and you realize that what people argue is that you should do this calibration in lieu of actually having all this physics that we are not including, that we know are important, and perhaps resolution. But now we have 5 parsecs, 10 parsecs, 20 parsecs. We should start to be resolving these self-Taylor explosions. We should start to be having less problems with the resolution. What are the other things that we've been talking about? And we've been talking about these things for many, many decades now. And in the past 2 decades or so, we've been actually putting these things in models, and we realized that magnetic fields, cosmic rays, relative transfer, these physics that we know exist in our universe and we have a relatively good handle on, are actually going to affect galaxy formation. And so when we start to look at what they do to galaxies, perhaps that we don't know that well, but we start to have some sort of idea at small scales. Magnetic fields influence how molecular clouds form stars. If you start to look at galaxies, you see that it actually can affect how the stars distribute. You see in orange here how the star formation regions of the galaxy are shifting. When we look at the turbulence of the ISM, if you have very strong magnetic fields, you can suppress the turbulence. If you look at radiation, specifically in dwarf galaxies, because they have these shallow potentials, right? The radiation from stars is able to heat up the gas and kind of lift it up a bit against the potential. And actually having early feedback is very important in the simulations, also from the numerical side of things. Because if you have a star forming a dense cloud, and you heat up the cloud, then the supernova coming after can actually very efficiently evaporate that cloud and impart strong feedback. And now we have these cosmic rays that everybody's thinking about as well. You see the same galaxy without and with cosmic rays, and then you see these beautiful biconical outflows coming out of the galaxy. This is something that people have been talking about for a while, and then Phil was showing the other day how these halos get colder in the presence of cosmic rays. So all these three things are going to contribute to galaxy formation in very different ways. In some way, having just supernova feedback, right, it's like coming into your pantry and just having salt and having to cook something. Yes, it's going to turn okay, but it's not going to be as good as if you had all the proper spices to cook your galaxy. And yes, all my metaphors tend to be food related. But equipped with that idea, what I did was run this Pathfinder simulation, just a dwarf galaxy with all these different physics. You can see how all the galaxies were very different. And we found that actually this was kind of promising. And so the idea was to take this a bit bigger, right? Because the question that you always get when you run a simulation with a single galaxy is, yeah, sure, but how can you know? How can you know if these results that you found are just because of your individual galaxy? And what happens when you actually have a population? So these are the simulations that I want to tell you a bit about. These are my Azahar simulations. These are big just for the sake of the actual high resolution zoom region in a large cosmological box where we focus on having high resolution, about 20 parsecs per galaxy, and resolving the details of all these galaxies that you see here. You see the blue gas, the H1. You see the gray gas, which is the H2. You see all this radiation and the biconical outflows in some of the disks that pop up in the simulation, and so on. And so, as I said, the idea here is we have a large box. Here you see in the full zoom region, which is about 10 megaparsecs on this direction and about 8 or so in this direction. It continually shrinks because of the convex hull. And then if we focus just on the very center of the zoom, you see in the background that region, and you see how the galaxies start to emerge. In green, you're seeing the bubbles inflated by the cosmic rays as they push into the intergalactic medium. And we can continue to zoom in and just look at the very central galaxy here, and you'll see these other two companions coming in and merging with the central galaxy in a second, and they will develop this beautiful disk. And again, have these biconical outflows, primarily driven by cosmic rays. But one of the basic ideas of my work was trying not to calibrate things. If we get the galaxies wrong, that's completely fine. We want to have predictive power. And if you're going to do that, the other thing you need to have is not just the single simulations, but several simulations where you get to turn things on and off, so that you can assign specific effects to a specific physics, and you can actually understand how galaxy formation is proceeding. And so that's the idea with the suite, is 10 simulations, again, going from having no radiation, no cosmic rays, and no magnetic fields to putting all these things together. And so what that leads you to have, oh yeah, I remember what this is. What it leads you to have is, again, this large cosmological box with your whole galaxies forming in a box, but also the idea that you can have the same universe if you remove, for example, cosmic rays, or if from this one, without cosmic rays, you remove radiation, or you calibrate your physics to see what happens when you actually just have supernova feedback and you actually move the knobs up. And now you can do comparisons across all the galaxies and all the different systems popping up in the system, the IGM, but also, again, in detail for the same galaxy across different simulations. And so today I'm going to talk about the very first results coming out of the simulations, and just for simplicity and for the sake of time, I'm going to focus on 3 models. This one that I'll color in red, that I call HD, is the vanilla physics. It's just hydrodynamics without calibration. This one in pink is the calibrated model, and then this one on the right is one of my full physics. Full physics doesn't mean full physics. Perhaps I should call it the most physics. But it's the one that I want to compare here. So that gives you a bit of an idea of basically what is the difference between calibrating and adding more physics. And so one of the things that we've been thinking about in this conference is this UV luminosity function. And the idea behind it is that we can use that to basically anchor a bit our observations, our simulations with observations. And we can look at that across cosmic time, or at least down to redshift 3. And what you see is that actually we get a fairly good reproduction for this model in green, again with the full physics and with the boosted model. And as you go down and down in redshift, what you tend to find is that this one here with the boosted model is perhaps a bit low in luminosity, in this UV luminosity function. Oh, sorry. Yes. Is that too much? Yeah. Yeah, thank you. Perfect, yes. Maybe now you can see again. So the idea again is that if you just look at the green and the pink, you see that they provide a good match to the observations at high redshift, whereas this one without calibration is already overshooting in luminosity. I mentioned the pink is calibrated. It's calibrated to the galaxy star mass function. Sorry, I got the letters wrong there. And so what you can see in there is that once again that the red model without calibration is just overshooting and overproducing stars. But perhaps a bit more clearly, as a summary of the whole thing, is we can look at the UV luminosity density across redshift. And now we start to see a bit more of what is the difference between calibrating the physics and having all these extra processes and what that's doing to the formation of stars in our simulations. And so specifically what you see is that in the presence of cosmic rays and radiation, what you have is the feedback not being as efficient at early times for several reasons, but order zero, what you can think about is that the non-thermal pressure of magnetic fields and cosmic rays needs to build up in galaxies to get to the point of being equipartition or comparable to other force of pressures to actually be important in the evolution of the galaxies. Another reason that these things are actually evolving so differently is that the galaxies look dramatically different. So here you have the same galaxy, again, this is the one in the center of the simulation that I've been showing all the time, and you can see this beautiful disk here extended with star formation at the edges, and this more diffuse, a bit more yellowish disk in the non-calibrated model, and a smaller galaxy that is just non-clumpy, non-structured in the calibrated feedback. And I want to highlight here some work by a brilliant undergraduate student working with me that actually has been studying the growth of the galaxy. So one of the things that we want to check as well is how these morphological properties of the galaxies evolve across cosmic time. That's what Michelle has been doing. She's painstakingly been generating basically synthetic observations of every galaxy in the simulation, doing the proper PSF transformation, effectively translating the simulations into observables or synthetic observables. And I can't tell you about all the work that she's been doing, but one of the graphs that is my favorite is this one here, where she sample matches the simulation to the epoch's observations, and you see basically that we reproduce relatively okay the actual observations. One of the funny things that happens is that the model without any calibration seems to give us the best sizes, and the calibrated model here in the lighter blue has galaxies that are a bit too extended. The full physics is a bit too big. We still need to figure out why, so that's telling us again that there's more work to do. But another reason that the galaxies are different is that the star formation structure, the topology of the star formation, how it evolves is actually different. I'm going to skip this because it's a bit harder to see, but Tibor Dam, who was a student at Cambridge, recently graduated, used the simulations to see what happens as you include more and more physics. And here you can see how much you deviate from the main sequence of star formation, how much the star formation basically varies on short time scales and on longer time scales. And as you include radiation, for example, you see that the deviations are larger, so that gives you periods that vary both in short and long time scales. But then when you include cosmic rays, you suppress those long time scales, and that gives you sharper peaks of star formation. I'm going to skip this, but you can also put this in observational space. But another funny thing that happens is when you start to have more clustered star formation, what you end up having is more efficient outflows, particularly in the presence of cosmic rays. And that's what you see at high redshift. You see that our mass loading factors, again, the mass of outflows that you eject per stellar mass that you form, are higher than the non-calibrated model, actually in good agreement with observations. Same as at low redshift, when we actually find that these are a bit less dramatic because the star formation is actually ramping up. Although I would argue, I can go into a rant if you want me to, about why we shouldn't compare on this space. Another funny thing that happens with these outflows is that if you look at the distribution of the outflow in gas in yellow and escaping in red, and you compare with the other models, is that they entrain more less enriched gas. And so that's important because one of the most challenging, effectively, criteria or tests for simulations has been reproducing the stellar mass or the mass metallicity relationship. And so what you see is that now that we eject a bit more pristine gas in our outflows, we effectively retain more metals in our galaxy, and we get higher metallicities than the boosted model, and we actually reproduce the observations quite nicely here as well, and here as well. And in this slide, there is a little tip of another thing that is not coming out quite right with the simulations, and I might tell you if you ask me about it. But just with that, I want to just conclude by, first of all, presenting a bit of the simulations. This is what's coming. If you have any ideas, anything interesting that you think I should look at or you want to look at with the models, please let me know. But overall, I think the main conclusion is that we want to start thinking a bit more again about these magnetic fields, this radiation, these cosmic rays, things that we've known for a long while now that are important for galaxy formation. Thank you for your time. I'll take your questions.
Questions? This is beautiful stuff. Very cool. I just have a quick question. So, how do you, for the simulations that you do calibrate to the stellar mass function, how do you calibrate them? Because they're so expensive. So I'm just curious.
Mm-hmm. So the value that I use for the calibration is actually originally coming from Sphinx. these Sphinx models use this factor of 4, and so we run that down first. And the idea was to go as low as redshift as possible to get it right, but it turns out that it's relatively right from redshift about 8 or so, 876, down to redshift 3. So we just kept going, and 4 worked. Sorry, 4 meaning, like, again, like a factor of 4, stronger energy in the periodic supernova explosion, thermal energy.
Great talk. Maybe I missed this, but you showed that sizes were in better agreement with the uncalibrated model than the calibrated. Right, right.
Yes.
And so why is that? Can you explain that?
We don't really know yet. Michelle is doing some great work on actually looking at concentration of the galaxies and how they actually evolve across different tracks, a lot of parameters. And I think the current idea is that the models being with higher concentrations, somewhat higher concentrations, are reducing the sizes a bit more, whereas perhaps our non-thermal physicists maybe are puffing up the galaxies a bit. Having said that, the reason we reproduce this is not only because we are sample matching, but the other is because we're actually applying the PSF. Because when you actually remove the PSF effects, you see that the galaxies in the models, especially, sorry, like here, in the mass size relationship, at lower masses, fall down in size significantly. We're still thinking about this, but it makes me worry that, sorry, and the PSF size is here.
What redshift is this?
This one I think is redshift 3. So this is not the redshift that I kind of thinking about. Sorry, epochs is redshift 7, I think 8 and above. And so the idea then with epochs is that when we apply PSF effects, we see galaxies that are kind of the size of the PSF or slightly larger. If you remove the PSF, they're smaller. Makes me wonder whether we're still suffering from observational effects in these surveys.
Okay, I don't think we have time for more questions, so let's thank the speaker and all the speakers of the session.
Thank you.
So I'll hand over to Ken and Santi for the discussion.